Yeah, thanks for the kind introduction. It's a pleasure to be here to the talk, and thanks for coming to my talk. Today I'm planning to talk about my joint work with my great friend and colleague at MIT, Negin Gorezai, and then my colleagues at Google, Joshua Wang and Ashley Lobandioro, and Francesca Tuzan, who was at MIT, now she's at Baker. So this paper is about basically how you can transform offline greedy algorithms for sequential decision making to the online learning setting, basically transforming into online learning algorithms. And I'm going to talk about some of the theory that is required to develop this transformation and some of the application. So I've designed the talk so there's a combination of high-level ideas and technical details. So whichever tribe you belong to, whether you are here to learn about the problem and some of the high-level ideas, or you're here to learn about the technical details of the work, hopefully the talk has something to offer. Regardless, I'm hoping by the end of the talk I can convince you something interesting is happening in this paper, so you go and read the paper after. With that, let me jump directly into my talk. So this talk is really about sequential decision making, and in particular, I would like you to think about platforms where they receive a sequence of arriving users, and as the users arrive, they get to know more and more about the environment. So this paradigm, the sequential decision making, especially in operations, has a long history. Maybe it has its roots in classic applications such as airline revenue management, and then after that, in more classic applications these days, such as online retailing. But then with the advent of online marketplaces, it has found more exciting applications, I would say. For this call, I don't want to explain much, but you can think of different forms of shared economy, things such as ride-sharing platform, last-mile deliveries, food delivery, or you can think about applications such as internet advertising, internet software search, or display ads, or last but not least, you can think about cloud platforms and a couple of tasks that they do in real time, which can be very much fit into this application. Second, talking about either of these applications, probably for 1 hour, that's not what I'm planning to do. Instead, what I'm planning to do is focusing on one common aspect of all of these applications, and that's the fact that they try to learn and optimize as the users arrive, and as they get to see more about these users. And as they get to see about the users more, they try to optimize some sort of economically justified objective. It can be revenue, it can be user engagement, it can be social welfare. But what I would argue is that as they try to achieve these goals, usually most of these applications, they're going to face 3 fundamental challenges. So the first one is what I call the real-time decision making, in the sense that in many of these applications, the platform should make real-time decisions, and as a result of that, they have to face the uncertainty about the future. The second one is that in many of these applications, the environment for decision making is changing. So non-stationarity is probably pretty severe, and that is essentially what I call the dynamic aspect of these environments. And finally, in many of these applications, because of the combinatorial nature of the decision making, there is a computation complexity that the decision maker should figure out how to handle. The kind of the high-level agenda in this talk, not really like the research question I'm asking, just the high-level agenda is to develop generic tools for learning and optimization in such environments, such that in a computation efficient fashion, we can design algorithms that somehow go around these 3 limitations. Basically, given the online real-time aspect of the decision, given the non-stationarity of the environment, and given the combinatorial nature of the decision, we want to design algorithms that can learn and all. So this is pretty high level, so let me try to make things a little more concrete. So the 3 applications I would like to think about the rest of the talk are the following. So the first application is what I call the product rank. Imagine there is a platform that has different products to rank. It can be maybe a retailer, it can be maybe a recommendation system. And their task is how to display the product in usually a vertically sorted list in order to maximize certain objectives. It can be engagement, it can be revenue, it can be maybe even like fairness these days. So it's about ranking different products. And then the second application is assortment planning. Imagine you're an online retailer or even like offline store. And the question is, what items should you put in the shelf, subject to quote unquote shelf constraints, in order to maximize, again, a certain objective. It can be engagement, it can be probability of purchase, or it can be revenue. And the final application is what we call the reserve price optimization. In contexts such as the sponsor search, imagine I'm Google, there are advertisers, and I want to run an auction for different ad slots. Essentially, when a query arrives, you're going to run an auction, knowing the willingness to pay distribution of the advertisers. Your goal is to assign these ad slots to one of these advertisers in order to maximize the same revenue. And then I will run a simple auction. In this case, I want to run second price auction. But in order to boost the revenue, we are going to use personalized reserve prices for these advertisers. And the question is, how should you pick these reserve prices in order to maximize those? These three questions seem to be very different, but they are sharing a lot of common. So first of all, in all three applications, the platform are going to repeatedly perform these tasks. And they have to make these decisions kind of in a real-time fashion. So when you think about the product ranking and assortment for online retail, the real-time aspect of the decision is there. At the same time, the user behavior might change over time. And because of that, you have also the non-stationarity in the environment. So you see the real-time aspect and the time varying very much. The same as the sponsor search application, because advertiser bids for search query, they can change over time, depending on the many reasons. For example, advertisers outside option might change. So then the bidding strategy and the bids that they're putting on the same query might actually be different. And this is very much an online application because as search queries arrive, you would like to run auctions, and they're arriving over time. So you have, once the query arrives, you have to run an auction. So you need to make these decisions, for example, reserve prices in a real-time fashion. But more important than that, I want to focus on the computational aspect of decision making in all three applications. In product ranking, when you are trying to find the ranking of the products, essentially there are n factorials options, so you have to pick a permutation. So there are exponentially many options to try. In assortment planning, you're picking a subset, assuming a shelf constraint. The simplest one is a cardinality constraint. You want to pick a subset of size no more than k out of n options. And finally, in reserve price optimization, so when you think about that, I have, let's say, n buyers, and you would like to pick one reserve price for each. So even allowing for two possible reserve prices for each buyer, you have exponentially many alternatives to try. So the set of decision in all the three is exponential size. And it seems that even the offline one-shot version of these problems is computationally hard. And not only they seem to be computationally hard, actually under proper mathematical formalizations, you can show that all these problems are NP hard to solve exactly. In particular, when you think about product ranking, even for the simpler objective of maximizing the engagement, they have deep connections to maximizing what I call the sequential submodular functioning, which are known to be NP hard. Assortment optimization, for both the revenue objective and also for market share objective, you can show the problems are hard. The revenue objective is even more difficult than market share. Even for the market share, the problem has connections to submodular set function maximization, and which is known to be NP hard. It goes back to the classic work of Rad Niazadeh back in 1987. And the reserve price optimization probably is like the latest one that is known to be NP hard. So if you know the distribution knowledge, if you have distribution for value evaluation, and you would like to find the vector of the reserve prices that maximizes the expected revenue for second price option with reserve. There is this paper by Rafkana and Bond back in 2019, which establishes that this problem is empty. Right? So as a running example, the rest of the talk, I'm going to focus on maybe the simplest of these three applications, which is assortment planning subject to the cardinality constraint and for the objective of market share. And this problem is basically equivalent to submodular maximization. So let me try to formulate that problem so that I make sure that we are all on the same page. Any questions? So here's the problem. Imagine I have n products, and I'm going to define a function f of f, which you should think of it as the probability that you receive a click if you display a subset f to a user. Basically, a probability that the purchase happens. I'm going to call it a market share function. And most of the time, it's actually natural to assume that this function is monotone, because if I show you a larger set, the probability that the purchase happens is going to increase. But not only that, under some natural substitution properties, we can actually show that these functions, they have this property I'm going to call submodularity, which means that the marginal increase in the value of the function is going to be decreasing. It's an analog of convexity or concavity to discrete set function. And now, under the simplest shared constraint, which is a cardinality constraint, we can cast this offline problem as finding a set f that maximizes the value of f of s subject to the cardinality constraint k. And this problem is known to be n. So this is the offline problem. Let me actually tell you what is the online learning problem that I'm going to try to address it in this talk. So we have capital T number of rounds, indexed by T from 1 to capital T. At each round, the decision maker is going to pick a subset S of T of size no more than K. Once you pick the subset, then a buyer comes, is going to make a selection, and then you get some feedback from this interaction. So this feedback can be a full information feedback. In that case, you observe the function f of t at that time, which depends on the buyer that interacted with the platform. Or you observe essentially whether the purchase happened or not, or the probability of receiving the purchase given that particular set that you output. In this case, it's going to be f of t as well. So the first type of feedback, in the rest of the time, I'm going to call it the full information feedback. And the second type of feedback, I'm going to call it the bandit information. And regardless of the type of feedback, the reward that the platform received at that time is going to be the value of the function of the particular sets that you output in. Yes, please.
So in this formulation, so far, nothing couples like S of t across periods.
That's true. And throughout the talk, I'm not going to assume that anything coupled my decision factors. Yeah.
And then in terms of the information we observe, I could imagine one version is you just observe whether something's purchased.
Yeah. So
and that's a little bit different from observing like the probability that something is purchased.
It is. So it's going to be an unbiased estimator for this quantity. Trust me that everything I'm telling you in this talk is going to be translated into a setting that you only have that information. An unbiased estimator of the quantity of this. But for the simplicity, you're absolutely right. So I'm not asking that you get to see whether the purchase happened or not. I'm asking that you get to see the probability of purchase on the particular set that
I chose.
Yeah. Please.
Oh, I had the same second question.
No, this is technical terms, so I think. Cool. Yeah, so the benchmark that we are trying to compete with, knowing the entire sequence of functions ft from 1 to capital T, is what I call the best in hindsight benchmark, which is the best set that you could, best fixed set that you could pick with coordinate at most k for the empirical distribution, or in some sense, for the reward, which is the summation of FTs. All right. Now, many times, similar to the problem that we discussed, the offline optimization problem is NPR. And if someone tells you that this is the problem with NPR, this is not the end of the world. In fact, we have access to an arsenal of approximation algorithms to attack these problems. I can mention greedy algorithms, LP relaxation and rounding, primal dual algorithm, etc. And the type of guarantee that you usually get for the offline problem is that, hey, I have this algorithm that's going to, in polynomial time, return the set, let's say, whose value is at least gamma times what you can get under the offline problem. And sometimes you say, well, so these algorithms are probably pretty pessimistic because this gamma is going to be number between 0 and 1. But in fact, when you run these algorithms in practice, most of the times they have a much better performance than the performance guarantee that you see under the board. So you have some control over the open problem. But then the main catch is that the performance guarantee does not carry over to the online learning version of the problem. Simply because when you make the decision, you actually don't get to see the function. If you get to see the function and you pick the set that is approximately optimal, by definition, by linearity of the objective, you're going to be approximately optimal for the time extended version of the problem. But when you make the decision, you actually don't get to see the function. So you can't run this approximation algorithm. And as a result of that, the guarantee does not carry over. And in fact, you need to learn what is the best sequence of actions to play in order to be able to get any meaningful guarantee. But then, when you think about it, so let's say the step function optimization I told you about, when you're trying to maximize the market share. You have one alternative for every set of size k, so you have exponential many alternatives. And if you want to do online learning, probably you have heard two words, exploration and exploitation. Exploration means that I want to experiment, let's say a random option and try to learn from this experimentation. And exploitation means that knowing the information so far, I want to make the best decision that basically pick the decision best for my historical loop. So none of these two tasks is actually easy in this problem because first of all, exploitation is hard. You can't even pick the best given the information decision simply because the offline problem is really hard. So the time extended version up to any time t is going to be also really hard. So even like picking the best decision is a computationally difficult task. At the same time, because you have expansion in alternative track, by just randomly trying one alternative, you're not going to learn that much about it. So if in information theoretically speaking, exploration is actually a difficult task to do. So what makes this problem tricky is how you can actually do those two tasks given the fact that you have exponential AI. So there are many ways to attack this problem. So one way I would like to attack the problem is a problem. So even though we have exponential many alternatives, but at the same time we have access to approximation algorithms that are well behaved. And in this talk, I'm going to focus on one powerful family of approximation algorithms that turned out to be helpful in all the three applications I told you about. And that's what we call the iterative greedy class of algorithms. So what are these algorithms? So there is a formal definition for this family in the paper, so I'm not going to go through the formal definition. But intuitively speaking, it's a large class of algorithms that include greedy type algorithms and local search type algorithms, when you can decompose the problem into a bunch of sub-problems, where in each sub-problem you make a locally best decision, and then you put together these decisions together to find the final solution.
So could you say a little bit more about how that would work for the assortment optimization for market share?
So let's see how would that work for assortment optimization. So this goes back to a classic result by Niazadeh back in 1978, that the greedy algorithm is going to be approximation, the optimal approximation for this problem. There are many ways that we can describe this algorithm. Let me actually go with my weird language because this is going to be relevant to the rest of the talk. So what I'm going to ask you is the following. So imagine that you want to pick a set of type K that is approximately optimal at the end. I'm going to define K different sub-problems indexed from 1 to K. And these sub-problems are going to talk to each other. So imagine, as you see on this slide, so you have this line graph where sub-problem I is talking to sub-problem I plus 1. And they're going to communicate, and at the end, they're going to come up with a set. So how would they communicate with each other? So I'm going to initialize the system with the empty set. Then for each sub-problem indexed from I1 to capital K, sub-problem I minus 1 is going to send a message to sub-problem I, which is kind of like the part of the set that has been built so far. And given this message, the task of sub-problem I is solving a local optimization problem. And what is the local optimization problem? Given the set so far, what it does is it picks the next problem, that's the next element that has the maximum marginal increase to the current set as I minus. So you fix the element j that maximizes the marginal increase in the function, and then it's going to append that element to the previous set. Okay. I'm going to describe this local operation in a slightly different language for reasons that we will clear later in my talk. So let's call this marginal decrease will have a notation for that. So delta f as I minus 1 and j. So this is the marginal increase in the value of the function when you start from the set s to per script I minus 1 and you append element j to that. Thinking of a vector yj, so think of a vector y where j's element is going to be marginal increase in the value of the function when you add element j. The thing about this vector, this local optimization is the following. So you basically solve a linear optimization over the n-dimensional simplex by finding a point x that maximizes x dot products with y. And then you sample the next element j star from the solution of this linear optimization. And then you add it to the sets. So obviously, from the first line, when you maximize or the simplex, you're going to put all the mass on the element that has the maximum marginal, and then you're going to sample from a points mass distribution. So really nothing is random, but let's actually stick with this formal way of doing this local subproblem for reasons that I'm going to explain soon. Right? So they solve these local optimizations, and then at the end, the last subproblem is going to return the set sk. And the classic work of Niazadeh shows that this period algorithm is 1 minus 1 over the approximation. And this is actually the best approximation that one can hope for with this problem. Doing anything better than that is not easy. Right. So what is the research question you're asking? So the question is, can we transform offline greedy algorithm similar to the greedy algorithm of Niazadeh et al. In a computation efficient fashion to an online learning algorithm so that we get what I call sublinear approximate regrets. So what is that notion? So remember, this was the benchmark, which is the best set in hindsight, the reward that you get under the best set in hindsight. Let's say gamma is a target approximation for this problem, which is the best approximation factor that you can hope for. For example, for submodule maximization subject to cardinality, gamma is equal to 1 minus 1 over e. Then I define gamma regret to be basically equal to gamma times the reward that you can get under the best set in hindsight, minus the total reward that your online algorithm. And our goal is design an online learning algorithm that gives you a sequence of sets that has sublinear in T gamma regret. So that's the goal. Is the notion of gamma regret clear? It is going to appear several times.
Sorry, is it important that gamma is specifically the kind of optimal offline factor, or is this well defined for any?
Right. So if you set gamma to be anything better than the best approximation factor that you can hope for the offline problem, then this is going to be a journey that is leading nowhere. Because if you can get approximate regrets gamma, then you can actually translate that for the offline problem. Just imagine I use the same function over and over again. So because it is empty hard to get better than some gamma star, so you should not hope for plugging anything better than gamma star here. Sometimes you might be able to go with lower gamma compared to gamma star with the hope of getting a better regret bound. That is some question that people study. But I think the best, maybe the ideal question that you want to answer is that if I don't want to lose anything on the side of the multiplicative approximation factor, can I still get the sublinear regrets?
And here, I guess it's important also that I'm choosing my set S, knowing nothing about F.
Correct. Otherwise, you could get 0 gamma by just running the approximation algorithm around.
So do you have here some supremum over FT or something? Because I could see like this can be very negative in some cases for some FTs.
It can be negative, yes. And that's actually one of the issues with the adversarial online learning in general. That in many, so getting negative regret is totally fine, right? So, so actually, so in many cases, when you run these algorithms in practice, actually most of the time you see negative results. Yeah, so nothing is stopping you from getting negative. Your intuition is perfect.
And then gamma is what if it's negative? It's like-
Yeah, even right, even like gamma one. Yeah, so the goal is to keep this low as possible. So I care about the upper bounds. So if you get negative regrets, that's good enough. Yeah. But one thing you can say is that if gamma is said to be gamma star and you get negative regrets, that means the instance that you're interacting with is very far from the worst case instance for that approximation. Like the empirical distributions you're observing is very far from the points mass distribution on the worst case instance.
Right.
Otherwise, this will have nothing. Great. Right, so this problem, nothing specific, but this business of trying to say something about the online problem given access to approximation algorithm for the offline problem has been studied. Probably the first paper that studies something similar is the classic work of Kale and Vempala back in 2005, where they asking the following question. So in a linear optimization, if I have access to an exact oracle that can solve my offline problem exactly, can I transform it into an online learning algorithm? And the answer is yes. So in a very general class of problems, basically online linear optimization, as long as you have access to the separation marker or the set of decisions that you're making, an exact oracle can be transformed into an online learning algorithm. Not only that, if you're doing linear optimization and you have access to an approximation algorithm, there is a beautiful paper of Kakade, Kalai, and Liggett back in 2009, that they basically have a recipe. It's a black box reduction from online learning problem to offline learning. So you can use the approximation algorithm to get sublinear regress and preserve the same approximation value. But these results are very much restricted to the class of linear optimization. So if you go beyond linear optimization, there is this negative result of Hazan and Cohen back in 2016 that basically says that no black box reduction in the most general setting exists. So if I give you just some approximation algorithm for the offline problem, you can't use it in a black box fashion to get the solution for the adversarial online learning in the most general setting. It's non-linear objective. For the linear objectives, the reduction exists. And our paper fits into this picture in the sense that we are considering class of approximation algorithm. We don't put any restriction on the objective. The restriction that we put is that you have access to an iterative greedy algorithm that is solvable. And that brings me to my main result. So the main result of the paper is this one. So we show how we can design an efficient framework to transform offline iterative greedy family of approximation algorithms to vanishing regret adversarial online learning algorithm using Blackwell approachability. Our final result is that we can get a vanishing approximate gamma regret. And in particular, for the full information setting, you can get a regret bound, which up to T factor is optimal, it's going to order or tilde of the rest square of T. And then for the bandit information is or tilde of T to the tutor, which you can show this is also information that is optimal for this particular problem. But we need two conditions to hold for the iterative greedy algorithm, which I'm going to call them robustness to local errors and Blackwell locality or Blackwell reducibility in the paper, which are essential for the reduction to work. Our reduction is not a black box reduction, it's actually a white box reduction, in the sense that we look at the algorithm and how it operates, and we try to transform it into an online learning balance. And I think the technical result is interesting. One thing that excites me about this paper is what I call the power of the framework, in the sense that it can identify simple and generic conditions under which such transformation exists. And not only that, it turns out that actually these conditions, they hold in a large class of problems that at least I care about in revenue management, in market design, and also in combinatorial optimization. So there is a full list of problems in which you can find a pair of iterative greedy algorithms, so at least you can find a pair of iterative greedy algorithms and problems for which the two conditions are satisfied. In particular, the three examples I told you about. they have iterative greedy algorithms that are approximately optimal, and also they satisfy the robustness of local error and lack of locality. And there is a list in the paper. You can go there to see other problems. The one I'm planning to do in the remaining almost half an hour is to sketch some of the technical ideas and tell you how we can actually get these results and what are these conditions. Question?
I think this was asked before, but how are in the maximizing market share problem, how are the different time periods, the NXT, how are they linked?
They are not linked. Yeah. So think of a problem that you're allowed to pick any set of entity. So there is definitely a version of the problem that you can maybe have a capacity constraint access time to link these times. This is not what you're studying.
But I guess the link in some sense is that your benchmark is the best fixed action in hindsight. And so that's sort of.
That doesn't couple the problems you're solving. In some sense, the benchmark depends on the entire sequence. But at the optimization level, you just want to find a sequence that optimizes this function. The actual optimal solution is picking the best step for each of these times. So there is no capacity constraint or inventory constraint that couples this time. There are variants of these problems. So for example, the simplest one is bandit with knapsack in combinatorial environment, where you have some knapsack constraint that links this time. But imagine in the assortment planning problem, you have an inventory constraint on the number of items. And then the question is, how would you optimize? That's going to be a much more difficult question in the adversarial online learning setting, and we are not.
But I thought the benchmark was that the same S was used for every T.
That's true.
So it is the same.
No, so the benchmark is the same set. I'm just saying, if you just want to optimize the objective of the algorithm in the full information version where you know the entire sequence, nothing is going to stop you from picking the best set for each time. So the problems are not really coupled in any way.
So the benchmark, you're forced though to have the same set in every period, whereas the problem you're going to solve allows you to have a different set in each period.
That is true.
And that's why you might get negative.
Yeah, and you can think of it as, so I'm not making any assumptions on how the sequence of functions are generated. To just give you some intuition, imagine that there was an underlying distribution from which these functions have been realized. Then when you think about the best set in hindsight, this is essentially the Bayesian optimal benchmark. As T grows to infinity, by just applying a concentration inequality, you can say it converges to the Bayesian optimal benchmark. So in that sense, my benchmark is the Bayesian optimal benchmark in the special case that you have IID variables, but I'm not making such an assumption. I'm just assuming that you have an arbitrary sequence of functions, and my benchmark is the best set in mind.
So you said your result was like vanishing gamma regret. So it's the gamma like for the optimal gamma for the offline thing, or like?
Yes. So for most of these problems, the gamma is the optimal thing. In some cases, like here, this gamma equals to 1/4. For the bandit version of one of these problems, this is probably not. This is not the optimal gamma. But in most of the results in the paper, including the market share maximization, the gamma is the one.
So it's not like I have for the offline problem, I have a gamma approximation algorithm. I can convert that to a problem for the online setting with the same gamma. So when you say offline,
so most of the results in the paper, we preserve the gamma. So it's the same gamma as the gamma that the approximation algorithm is doing. But one thing you can do is that they have let's say half approximation, but you shoot for 1/4 gamma regret. I'm not showing any of those results in this part, but yeah, so we have some examples in the paper in which the approximation factor of the online learning algorithm is not the same as the approximation factor of the.
So your white box reduction doesn't necessarily preserve the gamma.
Yeah, so the version I'm going to show you in this talk, which is the vanilla version, this is approximate preserving, but there are some versions in the paper that are approximate.
You're not making any assumptions on the functions other than monotone and submonotone.
You need them to be bounded. That's the only assumption. Yeah, so I think the right way of looking at this result is that I'm not even making the submajority assumption on the function. That's just an example. What I'm assuming is that the offline problem is solved by an iterative greedy algorithm, where the algorithm satisfies two constraints: the black hole locality and robustness to local errors, which I'm gonna formalize them now. Yeah, so just a recap, it was the greedy algorithm that I discussed for maximizing motion from major functions of the equivalent capacity constraint. So now let's think about the time extended. So you have capital T number of rounds, and each round you want to make a set. So thinking about the same architecture, so you have in each round you have k sub-problems that are going to talk to each other. Let's say in time 1, they're going to talk to each other after the set. Then time 2, they're going to communicate after the set, so on and so forth. Now, imagine hypothetically that in every round, when the subproblem I-1 sending a message to subproblem I, you could actually find the best local move. Basically, for that round, I could find the Z that maximizes the marginal value of the function. So that would be equivalent to running the Nemhauser algorithm in every round. And obviously, this is going to be giving you the right approximation factor. It's no regrets. So this is too good to be true. So it preserves the approximation factor, but it's too good to be true because in order to make this local, you need to know the function. But now I'm asking the following question. So what if I look at one of these subproblems across time, and then I say, so rather than this subproblem making a local move that is exactly correct, what if the subproblem can make a decision that is what I call almost locally best? So it's not locally best, it is almost locally best. And in what sense? In an average sense of time. Meaning that if I look at every single decision here, it's not actually correct decision, but if I look at these decisions in some average sense over time, it's actually the correct decision. So this is going to be the attack strategy. So we try to kind of get this type of guarantee for every subproblem separately. And now here's the question number 1. So how we can formally define the meaning of almost locally best on an average sense over time? That's the first question. And the question is, once we formalize this, how we can actually obtain it using an online learning algorithm. It turns out that the answer to this question is related to the notion of black hole approachability, which was introduced by David Blackwell back in 1956. And the condition that we impose on the greedy algorithm is basically allowing us to reduce the online learning problem that the subproblem is facing to an instance of what I call black hole sequential gain, which I'm going to formally define soon in the talk. And then by basically using an algorithm for black hole approachability with some caveats, you can perform that task in an almost locally best fashion on an average sense. That's question number 1. And then question number 2, how we can glue these pieces together to obtain the final result. And then the answer is what I call the robustness of local error. Because when a subproblem is making an error, then this error might propagate. So you need some sort of condition which says that a small mistake at each iteration of the greedy algorithm is not biting you that much. Basically, it's going to bite you as much as the mistake itself, so there will be no error propagation. And not only you need the local robustness to errors, you actually need the extended robustness, which means that not only errors that are small at every time, but actually errors that are small at an average sense over time, they should not propagate in the analysis. They should not get out. So in the rest of the talk, I'm actually not going to talk that much about the robustness to local error. Trust me that this is an easy condition to satisfy, and almost all the iterative greedy algorithms that I have seen in any applications that I have interacted with satisfy this property. The one that is more interesting is how you can cast the online learning problem of the subproblem into an instance of black hole approachability, and this is basically what I'm going to do in the next 5 minutes or 10. All right. So if you haven't been following me in the last 10 minutes, I think this is the right time to tune back. So think of it as a mini course inside the talk, which is about black hole approachability. And if you want one takeaway from my talk, I think this is a beautiful result. Has a lot of applications. And hopefully you see how it's connected to the rest of it. So what is the black hole game? The black hole game is a 2-player game played between two players, player one and player two. Imagine player one picks a strategy X from the curly X, player two picks a strategy Y from curly Y. And this game has a vector A. So let me formulate it more. There is a target set S in a d-dimensional space. And then there is a mapping R, which should be bi-affine in the pair of strategies of the two players, that maps the pair of strategies into a d-dimensional vector. So two players, it's me and Chris. I'm going to pick X, Chris is going to pick Y. There is a bi-affine mapping that maps our strategy to a d-dimensional vector. There is a d-dimensional target set, which should be convex and compact. Now, my goal as player one is to pick a strategy that will land in the target set, the bi-affine vector payoff to be in the target set. And Chris's strategy is to pick a Y that we won't land in the target set. That's a one-shot game. You can think of it as a zero-sum game played between us. So I get one if we land in the set S, and Chris gets one if we don't land. Now we can think of a sequential version of this, which is called Blackwell sequential game. It's a repeated version. I'm going to play this game sequentially with Chris. I'm going to play X1. Chris is going to play Y1. We play, we get to see whether we land in S or not, and then we repeat for capital T number. And then my goal as player one is to basically try to have a strategy developing a sequence of actions X1 to X capital T, such that regardless of what Chris does, on average, we approach to target set S, which means that the average vector payoff gets closer and closer to the target set S. So this is the notion of Blackwell approachability. So we say a target set S is GP approachable if player one has access to a strategy, which means that I can devise a sequence of actions X1 through XT, such that for any choice of the other player's strategy Y1 to YT, the average vector payoff in terms of some distance gets closer and closer to set S. Meaning that the distance of the average payoff on S is at most G of T. And think of G of T as a function that converges to 0 as T goes in. Yes.
So technically, I don't really need to get into S. If I just circle it, I still win, right? If you circle it, you still win.
Yeah, you do. Yeah, I mean, by circling around S,
Yeah, the average
you
is
get
inside S.
closer, you know, in sense of the distance, infinity distance. You can't just go around it with a constant distance, because then this average number is going to be constant. So you want it to converge to 0. So you need to get closer.
But my average reward can be inside S, even if I'm always far.
Yes, that is true.
A million miles north, a million miles south all the time.
Absolutely. Absolutely. This is not the last iterate coverage. This is the average thing.
You get further and further away at each iteration, right?
You can be further and further away at each iterate, but on average it's very fine. And this is why, for example, in the problem I told you, I need almost locally best on an average sensitive time. I don't need my last iterate to be a good decision. All I need is that on average at every day. Good. The different norms can be used here, and because of that, you need different algorithms. So the L2 norm version has been in the original work of David Blackwell, 1956. And for reasons that we explain in the paper, we actually need L infinity. Further developments show there is an intimate connection between Blackwell approachability and online convex optimization. In fact, there is a two-way reduction between the two problems. Having an algorithm for online convex optimization, you can have an algorithm for Blackwell approachability, and vice versa. And let me tell you like a beautiful theorem which is going to be relevant. We say a convex set S is attainable in this problem or satisfiable if for some reason player one has access to a magical strategy, which means that there exists a strategy for me that regardless of what Chris does, we are going to land in this particular S. This seems to be too good to be true and does not necessarily hold in instance of this problem. There is relaxed requirements which are called response satisfiable. So this is basically saying that Chris can go with any strategy, he can go first, but then I already have a strategy that can respond. Basically, for every strategy Y, there exists an X that guarantees that I'm going to land in the target surface. And then there is another requirement which seems to be slightly stronger than the previous one. It's called half space satisfiable. So this is saying that if you look at target set F and think of any half space, its intersection with target set F, then that half space that the half space containing set F, that half space should be satisfied. Basically, for any half space that contains F, there should exist a magical strategy. Okay? They still a little bit stronger, but they're still not as strong as the first one. So this is the useful theorem of David Blackwell, that a convex set F is approachable in L2 if and only if the set F is response satisfiable. So if you have the second requirement, it is if and only condition for approachability. And in fact, thanks to algorithms in online linear optimization or online convex optimization, there exists approachability algorithms where GT is equal to the order of the diameter of this space, the space of vector payoffs, divided by a square root of it. And then there is a Blackwell's equivalence theorem that says approachability is equivalent to response satisfiability. It's actually equivalent to half a space satisfiability, which is quite nice. All right. So just one caveat, in the paper, we actually need L infinity distance version of the Blackwell approachability, which did not exist in the literature. So we had to use a reduction to linear optimization with a certain follow the regulator algorithm with a strongly convex regulator based on the dual norm of L infinity, which is L1. I actually think this is kind of an interesting piece in the paper. That if you are into optimization theory and you wanted to think about the Blackwell approachability in L infinity distance, I think it's something interesting that we can look at. So now let's see how this fits into my term. So this is the problem. So we have these sub problems, and as a recap, sub problem I minus 1 is sending a message to sub problem I, and sub problem I wants to find the best local moves below. So we say an iterative theory algorithm like this is going to be Blackwell local if the following gadgets exist. Think of player 1 in the Blackwell sequential game as the player who is picking the strategies BI. Think of player 2, the adversary, who is kind of a hypothetical player, it's not a real player, that given the function at time t and the previous set fi minus 1, is giving you a vector 1. This is pretty abstract. And I don't require this player to play in my algorithm, just like a hypothetical player. Also, I needed by affine function R exists, which maps the pair of the strategies vi and y to a vector payoff. Also, I'm going to endow the algorithm with the convex compact target set S. And this is the final requirement I need. All these gadgets should be designed such that Vi in my greedy algorithm is the best local move only if and only if the bi-affine vector is in the target set S, given the pair of Vi and Y. So if everything that is here on this slide holds, then we say that iterative greedy algorithm satisfies Blackwell local. It seems to be a weird requirement, so let me actually show you why this algorithm is going to be Blackwell local. So this goes back to my way of writing down this requirement. So remember, Zi was basically the point in the n-dimensional simplex that maximizes x dot product y, where y was the marginal increase in the value of the function where you add different elements. So the jth coordinate of y was the marginal increase in the value of the function at time t, where you add j. And importantly, in this online learning problem, you don't have access to y. That is going to be how it is related to Blackwell approachability. As player 1, I don't get to see player 2's strategy, which is y. And before getting that, I have to actually make a decision on what to out. Right? So here's how things fit into the Blackwell sequential game framework. The space of a strategy for player 1 is n-dimensional simplex. For player 2, given the function at that time and the previous set, is going to pick a vector y, where the j coordinate is equal to the marginal increase in the value of the function. Now, my bi-affine vector payoff is going to be defined the following way. It's going to be the dot product of x and y minus the j coordinate of y. So this is the j coordinate of the bi-affine vector payoff. So x is going to be the distribution of our elements. Y is going to be the vector of the marginal increase. And the jth element of the bi-affine vector payoff is the dot product of x and y yj. And then the convex target set is just the positive ordinate. In that sense, if r is greater or equal than 0, then you can say x dot y is greater or equal than yj for every j. So this is equivalent to saying that x is the point mass on the coordinate of y that has the maximum. Right. It was a very simple reduction. And this is actually why I picked it for the sake of this stuff. Right. So this is the last thing I said. The vector payoff R is going to be the set S if and only if X is the point mass on the coordinate of the marginal vector that has the maximum. Cool. So that means the local move can be cast as a Blackwell sequential game, and this is going to be basically the final output. So I'm going to run separate instances of algorithms for Blackwell approachability, one for subproblem 1, one for subproblem 2, and then the last one is for subproblem k. These algorithms at each time are sequentially making their decisions. And imagine that they're online learning algorithms, so they don't need to get to see the adversary's strategy in each round. So they make their decisions, then they're going to communicate those decisions. And at the end, the last subproblem is going to output the set. This is basically the final output. So there are a couple of details I'm swapping on the rod. The one is that in Blackwell sequential game, after Chris and I will play each round of our game, there should be a feedback for me as the online algorithm to make the right decision in the next round. And that feedback is the vector payoff from the previous round. So you need to generate the vector payoff in the architecture I showed you in the previous slide, which is something that you can do. Like, for example, for the submarginal function, knowing the function, you can create a marginal, we can feed it back to the Blackwell algorithms to get to see what is the vector payoff in the previous round. And then the analysis is done by basically putting the guarantees of the Blackwell algorithm together with the robustness to local errors, and then this essentially gives you the final answer. I'm not going to go through more details. So robustness to local errors is basically the assumption that you need in order to put together these error bounds and get error bound. All right, so this is the main theorem. We can get order square root t up to large factors, approximate gamma degree for large class of problems. And this is the polynomial time algorithm. I think it's some sort of an interpretable algorithm in the sense that the structure is clear. So you divide the problem into subproblems, and then for each of them run an online learning algorithm. And it's actually quite fast because the local tasks are usually easy subproblems that we can solve in an online learning fashion. So putting them together is actually quite fast algorithm. All I told you about is the full information version. When you think about the bandit information version, you need to first think about the bandit version of the Blackwell approachability, which is something that hasn't been studied before. There is a problem we defined in the paper called bandit Blackwell approachability, which is basically the same problem as before, but at the end of each round, I'm not gonna get to see the vector payoff. But then I have the option of announcing a particular round to be the exploration round. In that round, I play something, Chris is gonna play something, and I'm gonna get to see the vector payoff, but I get no reward in that round. Basically, that round is not gonna be counted in the average reward at the end. So it turns out that if you can solve this problem, then you can use that algorithm for the bandit version of the offline to online transformation. And we designed an algorithm for this problem in the paper, which I'm not going to talk about. And yeah, so putting all together, you get Similar type of result for the bandit version. There is going to be a lot in the dependence on t, which is order t to the 2/3 order. And yeah, so we ran some simulations on real-time data that we got for these applications. In the interest of time, let me actually not dig that much deep into them, but back to your question. In terms of that, when we ran these algorithms on the real data, most of the time we got negative regrets. In some sense, the design is where the worst case instance, but the algorithm structure is probably powerful enough that can pick up the pattern in the data and can do much better than the upper bound of the regret that they showed you. In fact, maybe negative regrets. And this is the universal phenomenon. Right? Every single paper I have written down with just adversarial learning, when you run the algorithm on data, you get it. I think someone should probably write another paper on why this is the case. I think the reason is clear. The benchmark is the best in hindsight benchmark is very pessimistic, makes no assumption on how the input instance is generated. So as long as it is IID, usually, so if you run these algorithms on IID data, for example, then you don't get negative regrets. But if it is non-stationary and it's not IID, then somehow the algorithm magically picks up the pattern, performs very well, but the benchmark doesn't perform well. There are some refinements for the best in hindsight benchmark. For example, there is this K-switch benchmark that you allow the benchmark to switch K number of times, where K is a sublinear in T number, sublinear in T. Everything I told you can be actually extended to those settings. We don't have them in the paper, but this is kind of like a straightforward reduction. All right. So with that, let me try to conclude my talk. I think the main takeaway message is that there are certain problems ranging from memory management to computational optimization that you have access to local search or greedy type algorithms that are approximately optimal for the offline version of those problems. You can use our recipe as long as the iterative greedy algorithms are robust to local errors, and you can also somehow cast the local task of those greedy algorithms into an instance of Blackwell game. So if you can do both of them, putting the two pieces together, you have a way to transform your offline algorithm into an online algorithm in computation efficient. So with that, I would like to conclude my talk. So you can find the link to the paper here, and that's it. Thank you so much. Any questions? Yes, please.
So you mentioned K-switch setting, but like the other thing is like we're looking at like so this is kind of like the external regret version.
Yes.
Where like you can look at the swap regret or
Yeah.
another regret.
Yeah.
So doing those.
Yeah.
Like,
So Chris is talking about what people call dynamic notions of regret. So there is external, the swap regret, there is external regret. I think I haven't studied those, so I don't want to make a comment on that, but I have a feeling that some of the machineries here can be applied to the version of the problem where you are targeting swap regrets. But yeah, so I don't see any fundamental reason that changing to dynamic regret is going to make any difference. But yeah, so you can chat about it. We don't have any results that speak to that.
but is it weak? Is it that seems stronger than the K-switch regret, which only allows you to do
It is. No, that's true. The K-switch is an immediate reduction. For swap regret or external regret, I think you need to be careful about some parts of the analysis. But here's the thing. So the tricky part is the robustness to local errors. Because the online learning problem of each of these sub-problems, you can run an off-the-shelf algorithm for swap learning. It's a little bit tricky because I don't think swap learning has been studied in the general context of Blackwell approachability, but it has been studied in online convex optimization. So if you follow the entire reduction from Blackwell approachability to online convex optimization and you borrow an off-the-shelf algorithm that targets dynamic regret for online convex optimization, it should give you something for Blackwell approachability. whether that results together with the type of robustness of local errors that we have can give you the regret bound, I think that's the question that needs to be carefully investigated. But I don't see any fundamental reasons that it's not going to work. But that's a great question.
Once you break your problem into the sub-problems, then your algorithm is very similar to several off-the-shelf algorithms, right? Especially for the bandit case, for example.
Off-the-shelf algorithm.
Like for, say, EXP3.
Yeah, so actually, that's a great point. So this example that we had in the talk, right?
Yeah.
Well, pick the item that has a maximum marginal increase. This is the linear optimization. I could run an EXP3 instead of using Blackbird opportunity. The reason I picked Blackbird opportunity is because a lot of actually these local optimizations are not linear optimization. Like we have applications in the paper where this locally best move is going to be the solution of a min-max game. So there is a kind of a saddle point optimization that you have to solve in order to get that. And their Blackwell opportunity shows its full power, but you're absolutely right that for the special case of Hauser et al. Algorithm, I could actually run an EXP3 for the full information. I could run multiplicative rate update for the full information version and get exactly the same results. Yeah, so Blackwell opportunity doesn't show its power here. So I picked that as a running example for demonstrating the framework, but really like the power is going to be in some other problems. Yeah, so in other words, I know local search algorithms that their local task is not really optimization, but it can be cast as a black object. And in fact, my last comment, if you think really carefully about it, there should be a way to cast them as a convex optimization, because Blackwell sequential game and online convex optimization are equivalent. The thing is, the reduction from Blackwell opportunity to online convex optimization is so complicated that sometimes when you look at the problem, it's hard to cast it as an online convex optimization problem. But when you think of it as a Blackwell sequential game, it is actually becoming very easy. And it turns out it's the case in several of the applications that we're studying. But that's a great thing. Yes, I'm just
curious if I don't know much about this. So if you have, I'll give you a comic set S and then the binary mapping R, is it easy to check if this is Blackwell possible or not? Is the problem itself like?
You mean checking the half space satisfiability computation?
Yeah.
If you have access to a separation oracle for that convex set, you can do this in parallel. Like detecting whether a problem is half space satisfiable. Forget about my talk. It's like Blackwell sequential game. So the computational problem of checking whether this is Blackwell satisfiable or not is equivalent to having access to a separation oracle for a client. So there are algorithms that, given access to a separation oracle, can tell you whether this is Blackwell satisfiable.
I see. It's like ellipsoid method or something? Or no?
It is pretty much similar to running ellipsoid, but on the dual of the optimization problem that you're trying to project into the steps. Think of the convex optimization and you're trying to project into steps. Think of the dual of that, running ellipsoid and the dual will give you whether this is. So yeah, you run ellipsoid and the dual, you run it for a capital T number of rounds. If the step becomes small enough, that means it is black enough. I mean, yeah. So it's kind of like 2 lectures in the course on Blackwell opportunity, but
cool.
More or less that's how it works.
Okay, well, thank you, Rad. Thank you.